Okay, today we're going to look at what's called the change of base formula. We've used a base of 10, we've used a base of e, we've actually used other numbers as bases as well, so for example log base 2 of 17 here. And back in the old days when our calculators weren't as advanced as they are now, we used to have to use change of base formulas to plug them, to plug something like log base 2 of 17 into our calculator. You don't have to do that anymore, thankfully, but it's important that you know how to do this because it helps for problem solving in other situations as well, and we'll look at those. So the way this change of base formula works is if we have log base a of x, like we do here, we can change the base. We can make the base anything that we want. So we can use a base of 10, we can use a base of e and use natural log. We can use, a base of 300. It doesn't matter. Whatever value we want for our base, and this x is going to stay up here. So notice we're going to have log base, usually 10 or e, whatever you're using, of x in the top, and then log base, that same base that you used in the top. So say log base 10 or log base e of a goes in the bottom. So the one that's the part that's on the is on the a bit higher up, I guess, goes on in the numerator, and the part that's a bit lower down goes in the denominator. Okay. So if we want to write log base 2 of 17 with a base of 10, for example, we can say log of 17 because that's the one that appears higher up when we're looking at it, over log of 2. And now they both have a base of 10. Okay, so when I was in high school, we used to have to change the base to plug this into our calculators. Like I said, now your calculators are sophisticated enough to deal with this notation already as it was. We could use the same thing. We could use natural log, for example, just to show you what that looks like. So natural log of 17 over natural log of 2 is equal to log base 2 of 17. And you can test this on your calculator. So you could plug in log base 2 of 17, calculate it. You could plug in ln of 17 divided by ln of 2, calculate that, and you will get the same answer. Okay, so just practicing these, we're going to change both of these to a base of 10 and a base of e. So log base 10, we don't even have to write the 10 of 8 over log of 2. And if we want, this is also equal to the natural log of 8 over the natural log of 2. If we want a base of e, here we'll have, for base 10, we'll have log of 10 over log of 3. And notice if we have a base of 10, if we were to simplify this, we're thinking in our heads, we're thinking 10 to what power gives me 10? And of course, we know 10 to the power of 1 is going to give us 10. So this whole logarithm, the entire numerator, is then equal to 1. Just if we're simplifying. Okay, and this is also equal to natural log of 10 over natural log of 3. Okay, so we're actually going to apply this. It doesn't work for every situation, but so in this first one, we're actually just reviewing exponential equations here. So 25 to the x, we've got 5 to the x. We can see that we can kind of think of 5 to the x as our variable here. So we can say we've got 25 to the x is the same as 5 to the x squared, right? And we're basically dealing with a quadratic equation. So let me rewrite this. We've got 5 to the x squared minus 3 times 5 to the x equals 0. And then we can factor out 5 to the x. So we've got 5 to the x times another 5 to the x minus 3 equals 0. And okay, so we're solving each piece here. So for this first part, we're thinking 5 to what power is equal to 0. And we know actually, well, that doesn't exist. There's no power that we can raise 5 to equal 0. So that part does not exist. Don't include that in your answer. Here we're going to get 5 to the x minus 3 equals 0. So 5 to the x equals 3. And we could just rewrite this in logarithmic form and plug it into our calculator. So we can write this as log base 5 of 3 is equal to x. And we could solve that in our calculator. Or we could take the log of both sides. So in this previous step here, we've got 5 to the x equals 3, right? We can take a log of any base, so we could use log base 10 of both sides. Then remember, we can bring down our exponent as a coefficient. So that's going to go to x times log of 5 equals log of 3, right? And then we can divide both sides. So we're dividing by log of 5, dividing by log of 5. Okay, so x is going to be equal to log of 3 over log of 5. And notice, so these are equal, right? Interchangeable. We've got log base 5 of 3 is equal to x, which is equal to log of 3 over log of 5. This is the change of base formula. That's where it comes from. So this is equal to this. Okay, and either solution would be correct. So that's your exact answer. If you wanted to get an estimated answer or a rounded answer, you would then plug that into your calculator and calculate it. Okay, so you could do the same thing with part B for that same problem, or that similar problem. We've got, we've got 8. Notice we've got 9 to the x and 3 to the x. So again, we're dealing with a quadratic equation. 9 to the x is 3 to the x squared, right? Minus 3 to the x equals 0. So we can think of 3 to the x kind of as our variable, and we can factor that out. Okay, and in this first part, we're going to get 3 to the x equals 0, and that's not actually going to give us any solution, right? Because there's no power. When we take 3 to a power, there's no way we're ever going to get 0. So that doesn't give us a solution. And then we've got 8 times 3 to the x minus 1 equals 0. Okay, and there we're going to minus 1 divided by 8. So we've got 3 to the x equals, or sorry, add 1 divided by 8. We've got 3 to the x equals 1/8. And then we can either take the log of both sides, doesn't matter what our base is, we could use log, we could use natural log, or we can just simply rewrite this in logarithmic form. So whichever you prefer. I'll just show you if we take the natural log of both sides. Then we're going to bring down our variables, so we'll get x ln of 3 equals ln of 1/8. Be careful to keep 1/8 in brackets when you do this. Divide both sides by ln of 3. And so x equals ln of 1/8 over ln of 3. Just one more simple thing here. We can write 1/8 as, well, it's division, right? 1 divided by 8. So we could even expand that if we wanted to, and we'd get ln of 1 minus ln of 8, right? Remember, when we divide within a logarithm, we can expand that by making it subtraction. And you should recognize by now that anytime we have a log of any base of 1, it's always going to be equal to 0. Because in our heads here, we have a base of e, so we're thinking e to what power gives me 1? And of course, that's going to be 0. So this is equal to 0. So if we just kind of wanted to simplify that a bit, we'd get x equals negative ln of 8 over ln of 3. We could also just go right into switching this, where was it? From this step, we had 3 to the x equals 1/8, right? We could right away write that in logarithmic form. So we can say, okay, we've got log base 3 of 1/8 is equal to x, and we could solve that, and you'll get the same thing. So if you calculate this on your calculator, or this, or even this, you'll get the exact same thing. And notice this is the change of base formula. So we've got log of 1/8 in the numerator, and we've got well, ln, but it doesn't matter what your base is, and log of 3, or natural log of 3 in the denominator. Okay, part B, or sorry, part A of the second part. So we've got different bases here. This is really where change of base comes into play. It's nice to be able to have that to fall back on. So we've got log base 4 of x cubed plus log base 2. So we've got different bases, and it's not like before we've been using, say, we had log base 5 of 25, where you can think in your head, okay, 5 to what power gives me 25? Okay, this whole thing is equal to 2. Okay, but we have an unknown now. So we can't just evaluate what that log is equal to. We can see, obviously, that 4 and 2, we've also got 8, which has a base of 2. We can see a pattern here. So let's look at what happens when we use change of base. I'm just gonna, oops. I'm just gonna move this down if I can. Okay. So part A here, we can rewrite this using change of base. So log of x cubed over log of 4. And you can use any base you want. You can use e, you can use 2, you can use whatever. It really doesn't matter. Plus, we're going to write this part using change of base as well. So log of x to the 1/2 is the same as the square root of x over log of 2. Okay, we can bring down our exponents as coefficients of our logarithms. And this is equal to 8. So we've got 3 log of x over log of 4. Log of 4 we can write as 2 squared, right? And here we've got 1/2 log of x over log of 2. We can bring the power down in front here as a coefficient. So we've got 3 log of x plus 1/2 log of x. This is over log of 2. This is over 2 log of 2. If we want these, notice we're dealing with fractions, right? If we want them to have the same denominator, we can simply just multiply this fraction over here on the right by 2. Okay, so now they have the same denominator. Now we can add them together and combine them as one fraction. So we have 3 log of x plus this gives us 1, right? Log of x over 2 log of 2, and that's equal to 8. And we can just combine our like terms. We have 3 log of x plus 1 log of x gives us 4 log of x in the numerator. And actually we can multiply the entire denominator over to the other side. So we've got 16 log of 2. And if you want, you could even put that power of 16 up, or you can leave it as it is. It doesn't really matter. I think I'm going to leave it because we're going to be dividing by 4. So we divide both sides by 4. We've got log of x is equal to 4 log of 2. And then if we get the log of the same base on both sides, remember we can cancel that, but we can't do it with this coefficient sitting in front. So we have to move our coefficient up now. So we've got log of x is equal to log of 2 to the 4th. So now we've got log of base 10 on both sides as one single logarithm on each side, and we don't have any coefficients in front, so we can cancel our logs, and we get x is equal to 2 to the 4th over 16. Okay, and all right, part B. I'm just going to erase this part. Okay, so similar idea here. Again, we don't have the same base, but we can kind of see they're related, aren't they? What is that log of? Log base 4. Oh no, it's cut off. Okay, so so this next one here, the question got cut off a little. Let's call this x. So again, we can use change of base because we don't have the same base here. We can see, yeah, there's a pattern with 4s, but it's the most easiest way, I believe, to go about solving this problem is using change of base. So we've got log of x to the 5th over log of 16. Here, we are dealing with numbers, so in our head we could think, okay, 64 to what power gives me 125, but unfortunately that's not a very easy thing to think about in our heads. So you can decide, you can leave that just as it is, knowing that, okay, this is just a number, or you could use change of base on that as well. I'm running out of space. Minus log of x over log of 4. Okay, we want all our x's on one side, so we're going to add this log of x over log of 4 to the other side. We can bring down our coefficient here, so we've got 5 log of x over log of 16. Notice here we've got log of 4 as our denominator. 16 we know is 4 squared, so we can write that as log of 4 squared. Remember, we can bring down that power in front as a coefficient, so we might as well do that now. And then we're going to add our log of x over log of 4 on the other side, and that's equal to log base 64 of 125. Okay, so we want to get a common denominator here. We can multiply our denominator by 2 and our numerator by 2, so we've got 2 log of x plus 2, 5 log of x plus 2 log of x gives us 7 log of x. This is over 2 log of 4, and that's equal to log of 64, or log base 64 of 125. Okay, we want to solve for x here, remember, so we can simply multiply 2 log of 4 over to the other side. And this is times 2 log of 4 or log of 16, however you want to look at that. Okay, and then we want to divide both sides by 7. So we've got log of x equals log base 64 of 125 times 2 log of 4. I'm going to write that as log of 16 because we can put that power of 2 back up above the 4 over 7. Okay, so let's calculate that. We get out our calculator and we can do log base 64 of 125 times log base 10 of 16. Okay, and then we want to divide that by 7. Okay, and good. So then we've got log of x is equal to this decimal. Okay. So to solve for x, we'll write this in exponential form. So we'll have 10 to 0.1997 is equal to x. So if we do 10 to our answer, we get 1.58 about. Okay. Okay, I believe this is the last one, yep. Okay, so we're going to solve for x exactly here. We've got 8 to the x is equal to, 8 to the x minus 5 times 4 to the x equals 0. Notice we can't write 8 with a base of 4, but we can write everything with a base of 2. So we can write 8 to the x as 2 to the x cubed minus 5 times 2 to the x squared. And that's equal to 0. And then we can look at 2 to the x as a variable. So we can factor, actually 2 to the x squared as a variable. So we can factor that out. We've got, 2 to the x squared. Okay. So here, we've basically got 4 to the x equals 0 when we factor this, or when we solve for each part, for each factor, and we know that doesn't exist. There's no power that we can raise 4 to that's going to give us 0. Here we've got 2 to the x is equal to 5, and we can either take the log of both sides, or we can rewrite it in logarithmic form. So we can say log base 2 of 5 is equal to x and calculate that on our calculator, or we could take log of both sides here and bring down our x, and we can say, okay, we've got x log of 2 equals log of 5, and then divide both sides by log of 2. So either way, you're going to get the same solution. Right, this is just that using change of base. Okay, that's all. Thank you very much.